Let's discuss the inner product spaces. This section in this chapter is pretty cool because it gives us a different perspective of linear algebra. Actually, it's where linear algebra is trying to go, and that is to look at subsets of a vector space. And one of the classic and most important subspace of a vector space here is called an inner product space. We introduce this space here in this class. There are other courses that you can take in mathematics that deals with other spaces that are very interesting. So if you and when you take, for those who are studying mathematics, when you take real analysis, you will deal with what's called a metric space, which has its foundation here. And then when you look at other dimensions in terms of topology and functional analysis, you will deal with spaces called Banach spaces and also Hilbert spaces, which also have their initial footing here from an inner product space. The Banach and the Hilbert spaces are indeed inner product spaces. They become subsets of the inner product. And what they do is they define the inner product in a certain way. We somewhat glance at some of those concepts in this section without actually claiming what they are. Maybe in the next section that I cover, I will I'll let you get emerged here, and then when I cover the next section, I may, if I remember, to kind of put in some of the other spaces that are out there that are very intriguing, that stems from the inner product space. So you have the vector space, which is the very big space that everything is defined. Notice that the vector space has 10 axioms that all vector spaces must satisfy. Within those 10 axioms, you have two major axioms. One is the closure with respect to vector addition. Thus, the four that follow must come under its heading. And then number 6, that I called M1, A1, M1, A1 the closure for vector addition, and then my M1 or number 6 for the axiom, the closure property for scalar multiplication, of which the next four follow suit. So within all of the vector spaces, doesn't matter if you consider the metric space, which is where calculus goes. So calculus for the integral, which is a measurement, and that's what we're doing here with the norm, this magnitude, we're trying to come up with a measurement. So in the idea of calculus, the goal is how do you measure those vectors? The vectors in calculus are defined as functions. So how do you measure these functions? We measure them using an integral. So here in the so-called subcategory of the vector space, of which we have inner product spaces, like I said again, way out there, metric spaces, Hilbert spaces, Banach spaces. The goal is these spaces must satisfy the 10 axioms that we covered for the vector space, but also we must define how do you measure length. That's important. What kind of length definition can be presented. In calculus, we claim that to be the integral. In analysis, which is where calculus comes out of, we claim that to be some kind of integral or some kind of metric, some kind of measurement. And then for the Hilbert and the Banach spaces, we're going to talk a little bit about that. here in this book, they don't claim exactly what that is. When I hit on it, I try to remember to cover it. If I do forget now, maybe in the next section, like I said, I'll just go back and just say, hey, we talked about this before, but this is what this is, which is pretty cool. And again, those spaces in terms of the Hilbert and the Banach spaces are named after those mathematicians, of which they had close connection to the English schools of thought. There, the history of mathematics. You had scholars from Germany, which we get a lot of the mathematics from, and then scholars from France. And then the German scholars were somewhat in consultation a lot with those who were in Poland, and those scholars who were in Scandinavia. And then you had the English, and then eventually the American school. The American school came kind of late, just because of the history of this country. When this country is founded in 1776 and going into the early 1800s, math was prime, and at its fullest height, in Germany, in other places in Europe. And also, you have the school from Russia as well. And it would be interesting, even at our college, to even have a course on math history, which is very phenomenal to be able to put all these pieces together. Why do we do what we do? Where did this come from? What were they thinking? What were they trying to do? And thus they get the ideas and the notions that we use even today. So at any rate, the definition for the inner product again. Oh, let me say this: in in calculus one, you dealt with the measurement for the length, and you call that the Riemann sum. From the Riemann sum, we take its limit and we get the integral. So, just want to put that out. Now, the definition of an inner product: let three vectors u, v, and w be vectors in a vector space V, and let C be some scalar. An inner product on V is a function that associates a real number. Here, this inner product, previously you probably called it the dot product, with this inner product uv, this guy is a number. So it takes vectors, and once it applies these vectors to its mechanism, the result is a number. So the inner product maps into the real space, into R1. It takes vectors from Rn, but the result of which goes into just the number line. Here, inner product must satisfy these four statements, these four axioms. I put the name of what they're called here, in terms of the first one. You look at that and you can tell that that's commutativity. The second one, it looks like the distributive property, and that's exactly what it is. It's the distributive property for vectors. We call that additivity. Number three, here we have this scalar that could be multiplied to the inner product, or that scalar may be multiplied to one of those vectors. Doesn't matter where it is, you can always just pull it out and say that it's a multiplier to the inner product. We call that the homogeneity property. And in calculus, you have not calculus, excuse me, differential equations. You have a section on homogeneity, and there, once you determine that that the function is homogeneity, you can use a type of substitution to solve the differential equation. Well, it comes from here. It comes from linear algebra, and I just put here that very same statement from differential equations, just to let you know where it comes from. Number four, positivity, that the inner product of a vector with itself is either positive or is zero if that vector is indeed the zero vector. Now, here's some examples of inner products. I listed a few of them. Somewhat took these directly from my old notes from the old textbook. Here, the first is the inner product for matrix. Let A be some invertible n by n matrix. Then the inner product of uv is equal to a times u dot product with a times v, which is the in terms of how that looks, especially with graphing calculators, is just the transpose of AV times AU. Um, Now, here in this section and in this textbook, we don't really use that, and so you don't have to worry about that in terms of how that works out. Most times, it just works out just to be this guy right here. So, somewhat of a lot to say about nothing. But at any rate, number two, let U and V be two n by n matrices. Then the formula, um, uh, this so-called U dot V, or the inner product of U and V, would equal here to the trace of U transpose times V. Also defines the inner product for matrices. This works out as the standard inner product. And here, what I call the standard inner product is this guy right here. So, for example, take the 2 by 2 matrix space. For example, we have two matrices from the 2 by 2 space. Then the inner product there of those two matrices is just A11 times B11 plus, and so on. Indeed, this can be extended to the n by n space. So, again, I think there was maybe a play or a short story written. I don't know if it was by Shakespeare or one of those guys back then. Where the title was something about a lot to do or a lot to say about nothing, right? Um, Number three, the standard inner product for Rn. Now, there are other inner products out there dealing with just straightforward vectors. The textbook has them. Even in the old textbook, they have them. I'm not going to cover that, and so I didn't even waste your time to even put it here. If you want to look at some more how they change them, basically what they want you to do is they give you some kind of definition of an inner product, but then they say, is this an inner product space? So you got to go back and show or prove that that particular inner product that's given satisfies these four axioms. So the inner product that is the standard for Rn, based on the Euclidean, inner product space. Here it's just a straightforward inner product. So we have two vectors, U and V, that's in Rn, and so the inner product here is given. So nothing that you have not seen before. Now, with the inner product, two things must be defined for the inner product space. In terms of, one, what is its inner product? How do you define it? And then secondly, how do you measure those vectors? So one, we have a definition for the inner product, and then secondly, we have the definition for measurement. Now, measurement, you call it the norm or the length or the magnitude, right? So let's see. So the inner product for polynomials, p sub n, let two polynomials b and pn, say little p and little q, then the standard inner product is given by this here, and also with its norm. So indeed, once you start looking at an inner product, there are two criteria. One, what is this inner product? And then here, and then secondly, how do you define the so-called norm or the magnitude? So the norm tells us how do we measure the vector, and then from the norm we can get the distance, right? Now, in calculus, we also consider on the space of all continuous functions on the closed interval from a to b. We look at this inner product. Here, this inner product has something to do with so-called Hilbert spaces and Banach spaces. And so, if you want to go and just Google Hilbert space or Banach space, you'll probably see some of these, some of this there would show up in terms of this inner product and also this norm. I'll try to come back in the next section for the intro and just highlight those. if I remember, right? So the inner product of functions now, f and g, is given by the integral, uh, integral of f times g dx on the interval from a to b, and the norm is taken from the inner product. So the norm of a function here, this norm of f is, that simply is the definition is just the square root of the inner product of the vector with itself. And so here, if we have the inner product of f times f, or f comma f, that becomes the integral of f of x times f of x. So that's how we get f square x dx. So a review of what we looked at in the previous section in terms of the length, the distance, and angle. There's a couple of problems here in this section where they ask you the same question and basically the same problem from before. So I think the more we do these kind of problems, the more it kind of sticks with you. So let u and v be vectors in the inner product space V. The length or the norm or the magnitude of u here is defined. The norm of u given there, and then the distance between u and v is given. The angle between the two non-zero adjacent vectors u and v can be found as the cosine, and we've talked about that. And then 4, two vectors are orthogonal when their inner product is 0. Further review, we talked about Cauchy-Schwarz inequality, the triangle inequality, and then the Pythagorean theorem. So let's now look at some problems, and this is what we've been waiting on, right? So again, this problem basically something that we really had in the previous section, so just thought to put this as a review so that you can compare once we look at some of the other inner products that are introduced for the first time in this section. The idea of how we solve would be the same. So this inner product of u and v is just very straightforward. That's the 0 times 3 plus 3 times 0 plus 2 times 2, and all we get there is 4. Then the norm of u is this square root of the terms squared and then summed. So we have 0 squared plus 3 squared plus 2 squared. So we get the square root of that 9 plus 4, and we get the square root of 13. The norm of v, looking here, is the square root of the 3 squared plus the 0 squared plus the 2 squared. So we get the square root of 9 plus 4 again, and that's the square root of 13. And then now the distance, which is the norm of u minus v by definition. So this is the norm of, let's do the subtraction, u minus v, 0 minus 3 is negative 3, 3 minus 0 is 3, and then 2 minus 2 is 0. So this is the square root of that negative 3 squared plus the 3 squared plus the 0 squared. So we get the square root of 9 plus 9, that's 18, and the 18 is 9 times 2, so we get 3 times the square root of 2. So nothing much there. Good review. Now in terms of, again, this problem is a review as well. We can look at, ask the same questions, but now dealing with polynomials. So I suppose we can look at the polynomial p with its components 5, negative 1, and 4, and then q as 0. Remember, there's no constant here. Then 1 and negative 1. So we look at the dot product of p and q. Kind of helps now. So this is 5 times 0 plus negative 1 times 1 plus 4 times negative 1. So it gives us negative 5. The norm of p is the square root of, look at the components of p. So that's 5 squared plus negative 1 squared plus 4 squared. So we get 25 plus 1 plus 16 under the radical. So that's 25, 35, 40, 41, the square root of 42. The norm of q, I'm looking here since we did that work. So this is 0 squared plus 1 squared plus the negative 1 squared. So we get the square root of 2. Then the distance between p and q is the norm of p minus q. So we look at p minus q as 5 minus 0 is 5, negative 1 minus 1 is negative 2, and then 4 minus a negative 1 is 5. So it gives us the square root of the 5 squared plus the negative 2 squared then plus the 5 squared. So we get 25 and 25 is 50 plus 4. We get the square root of 54. And so that's the square root of 9 times 6. So we get 3 times the square root of 6. All right. So now let's look at here this so-called inner product. And what they want us to do, the inner product is defined on this integral. When we deal with the space of functions, typically the inner product that's introduced is indeed this integral. So let's find the inner product of f and g. So this is the inner product. F is 1 and then g is 9x squared minus 1. So this looks like the integral from negative 1 to 1 of 1 times 9x squared minus 1, which is just that. So it's just a straight integral. So we integrate. So we get 9x to the third over 3 minus x evaluated from negative 1 to 1. Well, this is just 3x to the third minus x. Evaluate that from negative 1 to 1. So we get 3 minus 1, and then minus here the 3 times the negative 1 to the third, which is negative 1, and then minus this minus here, so that becomes plus, and this, we evaluate that at negative 1. So basically the function is odd, so they retain their signs, and since it's from negative 1 to 1, you just take one of these sums and then just say times 2 basically. But at any rate, this is 3 plus 3, we get 6, and then that's minus 2, we just get 4. So now the the norm, which the norm is defined as the inner product of f is the square root of the inner product of the function with this f. So the norm of f. So what that gives us is this norm of f is equal to this square root of the inner product of f. Now f is 1, so this is 1 and 1. So this becomes the integral from negative 1 to 1 of 1 times 1, which is just 1 times dx. It's the square root of that. So we integrate 1, we just get x, that's evaluated from negative 1 to 1, and it's the square root of that. So this is the square root of 1 minus the negative 1, and that gives us the square root of 2. Do the same thing for g. Probably need some more space. So this norm of g is the square root of the inner product of g with itself. So this is the integral from negative 1 to 1. G is, see that inner product is defined here. So this is 9x squared minus 1 times 9x squared minus 1. We'll just say that's squared dx. And then this is the square root. Okay, so let's work this out. Let me add a page. So this is part C. We're looking for that norm of g, and so we get the integral from negative 1 to 1, 9x squared minus 1 to be squared dx, and that's the square root of that. So let's break that down. This is the integral from negative 1 to 1. We FOIL that out, so we get 81 x to the fourth minus 918 18x squared plus 1. This is dx, and then the result, we take the square root of that. So now we can integrate. So when we integrate, we get 81x to the fifth over 5 minus 18x to the third divided by 3 plus x, that's evaluated from negative 1 to 1. It's the square root of all of that. So this is evaluated at 1, we get 81 over 5. This 18 divided by 3 is just 6, so we get just 6 times 1 to the third is just that's just the 6, and then plus 1. Then we do the minus. Here is x to the fifth. If x is negative 1, it's going to be a minus, so we get minus 81 over 5. And all these terms are odd. So because they're odd, then they maintain their sign value. So this is positive 81 over 5. Negative and negative becomes still positive 81 over 5. So here we do minus this minus, so that becomes plus, and then 18 divided by 3 is 6, and then this guy is multiplied times x to the negative 3, which is x to the negative 1 to the 3, excuse me, is negative 1. And then it becomes minus this this x, but that's minus a negative 1. And all of that, we're doing the square root. So we keep on simplifying there. So we get the 81 plus the 81. So that gives us the 162 over 5. And then we get minus 6 plus 1. That gives us minus 5. And then over here minus 5, so that's minus 10. And then on our calculator, well, we can simplify this a little bit further. So this is the 162 over 5 minus 50 over 5. So that gives us the square root of, looks like 112 over 5. And then we can simplify that on our calculator. And where's my calculator? Now that 112 is 16 times 7. What about that? So we get the square root here. This is 16 times 7 all over 5. So that gives us 4 times the square root of 7 over 5. 4 times the square root of 7 over 5. So those guys, this takes a little while to work. It's just calculus, right? Which, when you come up to where I am, calculus is still algebra. So that's just algebra. So now we have this distance, which is the same thing as the norm of f minus g. Now that norm of f minus g is defined as the square root of the inner product of f minus g with f minus g. Translation is going to take a while to work all that out, right? So f minus g, the inner product of that with f minus g. So let's see. So here the f minus g is and we can probably just work that out here. F minus g is the 1 minus parentheses 9x squared minus 1. So that becomes 1 plus 1, so that's 2 minus 9x squared. Would have been nice if the ones cancel out, right? We just had a monomial, but no. My countryness comes out sometimes. So this is 2 minus 9x squared dot with 2 minus 9x squared. Okay, so we'll work that on another page. So let's do that, and I think we got it in terms of my memory. Let me add a page here. So we're looking at the distance between f and g, and that's that norm of f minus g. And we said that was the same thing as here the square root of the inner product of f minus g with f minus g. And that comes out to be the inner product of the square root of the inner product of, we get 2 minus 9x squared with itself. Okay, so what does that look like? that looks like here the integral from -1 to 1 of 2 minus 9x squared times 2 minus 9x squared, which is just squared dx, and that's all the square root. So we FOIL this out, so we get 2 times 2 is 4, we get 9 times 2 is 18, times 2 is 36, x to the second, plus 81 times x to the fourth dx, and this is all the 1/2 power. So now we integrate. That's a cool looking integral, I think, for left-handers, right? So here we integrate. We do not hesitate, we integrate anyway. And some of my old statements from a few years ago, you got to keep the students laughing, right? Well, they never laughed at that, but I don't know if they were even listening to me. Anyway, this is 4x squared minus 36x to the third divided by 3. We'll just put that there, 12x to the third plus 81x to the fifth all over 5. And let's see here, that's evaluated from -1 to 1, and that's all, can't forget that, the square root. So now let's evaluate these terms. So we'll plug in 1, so that gives us 4 minus 12 plus 81 over 5. And you can hear, since these are odd functions, we can just say times 2. It's the square root of all of that, right? And so you don't have to go through all of the rigmarole. Odd functions for the integral evaluated from 1 to -1 to 1. It's just times 2, and that's all the square root. So here, let's simplify that. This is the square root. We get that 4 minus 12, so that's just 8, which then becomes 16, and it's negative. And then here we have 81 times 2, so that gives us 162 over 5 minus 16. And the 16 times 5 is 80. That's what I thought. Just want to be sure. So it gives us the square root of 162 minus 80 all over 5. And that gives us here 82 over 5. So the square root of 82 divided by 5. So the square root of 82 over 5. Okay. So here, find the angle theta between the vectors. So you remember that one is going back to cosine theta is equal to the inner product of u and v divided by the norm of u times the norm of v. So first, three things we need. We need a little bit more than that, but one, we need the inner product. So we find the inner product, we find these norms, and then we can get the cosine theta, and then take the cosine inverse, and so theta is the cosine inverse of whatever you got here for this quotient. When they ask for the angle. So let's find the inner product first. So the inner product of f and g defined on this integral here is the integral from -1 to 1 of 3x squared times x squared dx. This is the integral from -1 to 1 of 3x to the 4th dx. So we integrate that, we get 3x to the 5th all over 5, and that's evaluated from -1 to 1. So we evaluate here this result, 3 over 5 times 1 to the 5th. And then, oh, that's a 3. I don't know how I keep missing that. That's funny. That is so funny. So that's to the 5th. So we evaluate that. That's 3x to the 6th divided by 6. So this is x to the 6th. 3 over 6 is just 1/2. Now it's even, evaluated from -1 to 1, even functions on a symmetric graph. That area would cancel out, you get 0. So here we get 1/2, evaluate at 1, and then this is minus, here this is 1/2, because x to the -6 is still 1, so we get 0. We said that when the inner product is 0, that implies that the vectors, the functions, are orthogonal. So f and g are orthogonal. That is, the angle between them it's getting between the end of between and the end of them to be the same. The angle between them is 90 degrees, or power of 2 radians, right? Now, a word on this very fascinating concept on the projection of a vector onto another vector. Basically becomes the projection of a vector on a space, which then in the long run can be seen even as a vector space projection on another vector space. So orthogonal projections in the inner product space. The projection of u onto a vector v is given here in the figure. So we look there. This is the image, the projection, or the image here of u onto, what's the deformed arrow, onto v. Now it's not all of v, so this image of u onto v is only here. We find it's perpendicular. So we call this length, this is not all of v, we call it a times v, where a is a scalar. So we multiply a times v, and it's going to shrink v, or it may even elongate v, depending on the angle. Okay, because if this guy is going the other way, then we'd have to lengthen v. So the projection of u onto v is a scalar multiple of v. That's what this a times v is saying. It's a scalar multiple of v. So let a be the scalar. So we can write the projection as the projection of here of u onto v. That's how we read this. The projection of u onto v is equal to the scalar a times v. Notice that the length of the projection is given. So the length is just taking the norm. By definition, we can take the scalar out, but it has to be the absolute value. And so here we look at this a times v. Let me erase all of this so you can see what here they're trying to do, and then afterwards I'm going to do what I'm going to do, because I think that what I'm going to do kind of makes a little bit more sense. Here I think, and this came right from the textbook, kind of leaves you hanging. I know it left me hanging. So here a times v is equal to u times cosine theta. What he's doing is, and remember this side here is a times v. He's taking the cosine of this angle. So the cosine of theta is equal to the adjacent AV divided by, and since we're talking about length, we can go ahead and just put that as the norm. It's the adjacent divided by the hypotenuse. So then that's how he gets the norm of AV is equal to the norm of u times cosine theta. So that's where this comes in, right? And so now from there, we look at this. He supplies, if you will, this v, this norm of v divided by the norm of v, and so that being supplied, here we have this this norm of u times cosine is equal to, you still see the norm of u and you still see cosine, and here's what he's trying to get at. The reason why he supplies this norm of v, you recall that the cosine is equal to the inner product of u and v divided by the norm of u times the norm of v. So if that be the case, that implies that the inner product of u and v is equal to the norm of u times the norm of v times cosine theta. So that's why he supplies this norm of v. You say, why does he do that? Well, he basically supplies a sophisticated one. The norm of v divided by the norm of v is just 1. Why does he do that? Because he has in mind this guy right here. Okay. So because of that, he gets then that numerator is this inner product. So the inner product of u and v divided by the norm of v. And it's now here what he's doing is you're only computing here the norm of AV, but the projection is just defined as AV. So basically you go through the task of removing the norm power to get what's on the inside, just AV. And so the norm of AV is this. He says, which implies that A is equal to the inner product of u and v divided by the norm of v squared is equal to that, and so thus he ends up with the projection of u onto v is what you want. Now personally, I'm good here, but he says which implies, then I'm like, okay, I don't think that's that obvious, not to me. Now here's how I prove it, and the way he's using geometry to get his results. We prove it by the method from linear algebra. And that was one of the issues that I had with this textbook versus the old textbook. The book that we were using by Anton was more theoretical in terms of trying to get you to see the classic view of linear algebra. Here, Larson is trying to move forward with a more conceptual vision of linear algebra in terms of engineering and physics. But I'm a mathematician, so let me show you what's really happening. So it's the same image, right? Here, the projection theorem, which is where this is coming from. And so in linear algebra, we take, what are we actually doing? What's the big goal here? What's the big space? What's the purpose? And then from there, can we put it all together? So W is a finite dimensional subspace of an inner product space V. It's just saying that W is a subspace, and we looked at that first section. We talked about a vector space, and then that second section. Well, this book is like it was 4.2, and then 4.3. We talked about the subspace. Is all we're saying. Then any vector U in V can be expressed exactly in one way. We call this a very classic theorem in mathematics, the so-called projection theorem. This plus is not the standard plus that you would think. It's actually a direct sum plus, which basically this whole statement here is, you may say, the Pythagorean theorem. So where U is the hypotenuse, so basically you get the hypotenuse squared is equal to each individual legs to be squared and then summed. So W1 is W sub 1 is here, and then W sub 2 is the perpendicular. So that's why we say here W1 is in W. What is W? W is said to be this subspace in the plane on the base. So this is W. And then W2 is said to be the plane that's in the perpendicular, that's going up and down. Kind of hard to draw that. Why can't we be friends? Why can't we be friends? So this guy is in the perpendicular. Well, W2 is in there, but that's the perpendicular, or the orthogonal complement. So prove that the projection of U onto W, or what we did, the projection of U onto V, here is what we want and what we're trying to get. And to erase this so I can actually prove this so you can actually see it. So since W and W2 are orthogonal, then we can write W sub 1 times, or the dot product of W1 and W2 is 0. So that's the key to trying to prove the idea of the projection. Now, here the goal is to prove the projection of U onto V is indeed the inner product of U and V divided by the norm of V squared times V. That's what we're trying to get. Now that denominator is just when you square that norm, you just get the inner product of V with V. So that kind of looks like more so how the author of this book writes it. So we're trying to prove that. That's what we're trying to end up with, right? And the only way you can prove it is to look at two concepts, to look at orthogonality, because that's what's happening, because you have a perpendicular, because you're trying to show that the image of this u is indeed this side right here. So that's the image. That's the image or the projection of u onto v. So here, I'm going to use black. So here, I'm going to call it W1. Let W1 equal to what we're saying, AV. It's that part right here, right? And W2 forms a perpendicular to W1. Thus W1 dot product with W2 is equal to 0. But by definition from the theorem, from here, W sub 2 is equal to u minus W sub 1. So note here that W sub 2 is equal to u minus W sub 1. So we have this dot product of W sub 1 dot with W sub 2. W sub 2 I write as u minus W sub 1. That's equal to 0. Now we take the dot product. So this implies that we have W sub 1 dot with u minus W sub 1 dot product with W sub 1 is equal to 0. But W sub 1 is defined as AV. So this implies then that W sub 1, let me just write it, this is W sub 1 dot with u, that's equal to, I'm going to add the dot product of W sub 1 and W sub 1 on the other side. So this is W sub 1 dot with W sub 1. Now I'm going to replace now the W sub 1 with what it is, that's AV. So I get AV dot with u is equal to here this W sub 1, which is AV dot with AV, which implies that I get AV dot with u is equal to a squared times v dot with v. Now I'm going to basically solve for a. So solve for a, I'm going to divide both sides by the a and divide both sides by this dot product of v and v. So, and then I'm going to write the right side first. So so this implies that we get a is equal to, I'm going to write this since v dot u is commutative, so this is the same thing as u dot v divided by the inner product of v and v. Okay. So now you can write this as this is the inner product of u and v. This is all over the norm of v to be squared. Now that's just a, right? So, but we said the projection of u onto v, see this guy is equal to, that's W sub 1. So here AV is is the projection of what you want. So, but the projection of u onto v is a times v. I get a, so a is this scalar. So a is this, the inner product of u and v. I'm going to write that as red. That's the scalar. Scalar's in red. No, it's supposed to be red. Red, red. Fred is dead. That's it. So this is u. It looks like a w. Man, I'm getting hungry. U dot v divided by the norm of v squared. V squared, not a dot or a tittle from Hebrew. Now that's just a, right? Times v. You get it? My phone is acting by itself. It's scary. The boogeyman, he's watching. So this is the projection of u onto v. It's the inner product of u dot v, or the inner product of u and v divided by the norm of v squared times v. So this part in red is the scalar. It's just a number, right? I think this illustration is a little bit better than what the author does over there. That is, as my African professor used to say in college, that is boo-boo. Let's move on. Here's the problem that we need, and then we're going to be through with this section, and then maybe I can get some turkey bacon and some egg white. Ah! So the projection, and I proved that so you can actually see what's going on to give you a visual of why the result is why it is. The projection of u onto v. Come on, v. Come on, Becca. So this is the inner product of u and v divided by the norm of v to be squared. I know the author here, he just says it's just the inner product of v with itself, and that's good. It's the same thing, times v. And then here he just reverses that. So you just interchange where u is with v. They just change positions. So we need a few things. Maybe I can write this right here. So this is the inner product of u and v over the norm of v squared times v. Can you see the 2 there? I can't, but anyway, I can. So we need the norm of u, which is, looking here, the square root. That becomes 4 plus 1 plus 4. So that's the square root of 9. We get 3. And then we need the norm of v, which is the square root of the 2 squared. I'm just going to put the results in there. 4 plus negative 1 squared is 1 plus 2 squared is 4. We get the same thing. And then we need the inner product of the 2 vectors. So the inner product of u and v would be that negative 2 times 2 plus that negative 1 times negative 1 plus the 2 times 2. So the negative 4 and the 4 cancels out. It just gives us a 1. So this projection of u onto v is the inner product, which here we get 1 divided by the norm of v to be squared. Well, it's just that what's on the inside. It's just 9 times v, and v is 2 comma negative 1 comma 2. That just gives us 2 over 9 comma 1 over 9, comma 2 over 9. Is that it? That's it. 2 over 9. That's what we got. We just do that. Just put the check there, right? Took my sins according to Job 14 and 17, and he put them in a bag, and then he sealed up the bag. Amen. Now the projection of, that's a good thing. It's a good thing for all of us. The projection of V onto U. So this is the inner product of U and V. Commutativity. So U, V, and V, U is the same thing. This is divided by the norm of U squared times U. Well, not U, but this U. U squared. Okay. So that inner product is still the same. So that's 1 over the norm of U squared. It's over here. So we get 9 times U, and U is that negative 2, negative 1, and 2. So that gives us negative 2 over 9, negative 1 over 9, and then comma 2 over 9. And that's what he gets, negative 2 over 9, negative 1 over 9, and 2 over 9. So that's it. So that'll get you through this section. There may be one or two problems that I didn't cover. They're exactly a match review from the previous section, so you should be good. Okay? So with that, I will say adieu.